works on this in the system. And what is really, really important of a Skupper is that all this inter-cluster communication occurs using mutual TLS, so it's secure. So you are just connecting all your clusters in a secure way and in a really transparent way, because it's just working at HTTP, gRPC, or TCP level. So we've got, for example, this clusters in Azure, in Google, in Amazon, and on-prem. We've got pods, we've got services. And what we need to do is just install a Skupper in all these clusters. So you just install a Skupper, and automatically will start happening some kind of MTLS communication between all of them. Okay, so all the traffic will be encrypted. So let me show you one really nice demo about this. You can find a demo in here in Red Hat Developers Demos Hybrid Cloud. This is a really simple demo, I know. It's just, okay, it's a hello world demo, but it shows you how powerful is a Skupper. I will need your help. It's here. This is the URL. If you want, you can. If you want, you can connect to this URL. Is hybrid cloud frontend default.apps.OpenShift. It's a bit big, but yeah, that's the URL. Yeah, I know, but it's easy. And basically, that's just a front end that I can send. For example, hello. I send a request, and I'm getting aloha hello. And here you see that the application or the cluster that get this request and send back you the response was GCP. Of course, I can just choose reverse. I can put hi, and I'm got it, and this. And all this logic is happening in GCP cluster. My GCP cluster is this one. This one is a Kubernetes cluster that is running in GCP, as you can see, for the host. And it's just running the front end and the back end. This is the front end, and this is the back end. Now, let's simulate a failure. Let's think like, what's happened if, for any reason, the node where I'm running the back end, it's failing. For example, it's failing because the disk was down. Maybe the network of this node was down. Maybe the whole cloud was down. So I'm just going to simulate this. For this, I'm going to scale it to 0. So I'm just removing the backend. There is no more instances, no more replicas of the backend. And now I'm just going here and just set Berlin. I do send a request. And now I'm getting Aloha Berlin from Amazon. The front end is still the same. It's just still connecting to GCP. But the traffic is automatically routed to Amazon. Why? Well, because I've got here my Amazon cluster. Again, you see that the interface is always the same. It doesn't matter if it's Amazon, if it's Google, it's always the same. And you see that I've got here the backend running. So what's happening is that a Skupper is, let's say, smart enough to detect that there is a failure and reroute automatically the traffic to the other backend, which is running in another cluster in Amazon. In fact, this Amazon cluster is running in New York, and this one, I think that it's in, I don't remember when it was that. I think that it was Frankfurt, but I don't remember. OK, in any case, you can see that a Skupper automatically makes this. What's happened when I recover? Suppose that I'm recovering, and oh, now Google Cloud is, or the instance of the backend of Google Cloud is up and running again. I can go, I can just select here Germany, and I send the request, and it's back to GCP. I'm just doing nothing. I'm just, starting and stopping everything, and it just recovers. Why this is working? Well, actually, it's working because we've got a Skupper router here. You see, this is the Skupper router. It's just the Skupper thing that we installed in each of the clusters. This is the Skupper router of the GCP, and I've got here the Skupper router of the Amazon. So I just install these routers and automatically detects these failures and reroute the traffic. A Skupper also supports other use cases. For example, depending on the latency. So you could configure Skupper to say, if the latency from this point to the other point, so from my front end to the back end, is more than these milliseconds, then just go to another cluster, things like that. So it can automatically detect which is the back end, which is close to the origin, and send there the request. Or also you could do things like, I'm just getting a lot of traffic to this cluster or to this cloud, and I'm going to start sending the request to the other cloud. So you can even configure to just monitor the throughput or there is a spike of the traffic and then start sending traffic to another cloud. These are all the kind of things that you can do with a Skupper. And you might say, but a Skupper probably is super complicated to use, and this is what you need to follow to just run. This is the example, okay? This is what you need to do. Just deploy your backend, but it's just it's a YAML file, a typical deployment file. Annotate it with a Skupper.io/proxy HTTP, so you're just enabling this backend as being Skupperized. And finally, in your main cluster, on one of the clusters, you need to init a Skupper and create a token. Basically, this token is used to secure the communication between clusters. And then in all other clusters, so for example, my main cluster was GCP. The other clusters, for example, Amazon, I just do a Skupper init again. So I just start all these routes. And I just say, connect to the other Skupper routes with this token information. And it automatically connects and do all this mesh for you. So it's super easy to use. And it's just a matter of running these CLI tools. Of course, some of you might say, and what's happening if you want to use GitOps? Skupper also supports, you can see it somewhere here, the YAML approach. You see it, I don't remember where, but there are examples. Well, now I'm just don't want to spend time here. YAML configuration. So you can just do exactly the same thing that I've showed you here, but instead of doing Skupper init, Skupper create token, and so on, you just do it by, you can see here in the example, by creating these YAML files, and then you can manage Skupper, but using the GitOps. Then, some of you will say, that's really cool, but what about cost? If I've got 2 clusters running, I need to pay double, because I've got my pods running in one cloud and some pods running in the other cloud. Yes, that's true, but for these reasons, we've got serverless. We know that serverless doesn't mean that we do not have servers, because we still have servers, but what it means is that we do not require server management. We just deploy the service, and all the cloud will manage everything. We'll manage the network configuration, how I would say the pod is, or the services, scale it up, scale it down. Depending on the traffic, just add more instances, less instances. All these things happen automatically. And that's important because it means that our cloud provider can only build for the exact demand, which means that if we do not have any demand, they cannot build for it because we are not running anything. Basically, in Kubernetes, we've got Knative to run our workloads in the serverless mode. Basically, Knative helps us to deploy Kubernetes workloads in a serverless way, which means that we can scale to 0. Basically, it means that if we are not getting any traffic, we can scale the application to 0. We can scale the pod to 0. If it's scaled to 0, means no memory, no CPU, or cloud provider cannot build for that. Of course, also, Knative can scale from 0. So the pod is there, but it's a stop. But when we get a request, automatically Knative will start a new instance. So I'm going to show you Knative in a quick demo so you can see it in action. I've got here how you define a service in Knative. You see that just defines kind of service, put here the type Knative, I set the image, the liveness proof, and the readiness proof, and that's all. No Kubernetes service, no Kubernetes labels, nothing. Just what I want to use. Now, I can do kubectl apply -f, serving here service. Okay, now, what is interesting, yeah, of course, here is the Skupper thing that I'm running. And the important part here is this greeter. You see that the container has been created, and now it's running. But I'm not sending any traffic. It's just there. Let's wait a bit. In fact, you can see it here as well. Let me refresh. I'm just waiting to not send anything so you can see how the traffic is automatically scaled down. You see here, you see that it's dark blue, which means that the pod, the deployment is there running. But by default, Knative, when the service doesn't get any request for 1 minute, it scales down. This is configurable. You could put 2 minutes, 30 seconds, 1 second, whatever you want. But you'll see now how the pod is terminating, and it will get in white. You see also here how the pod is terminating. So it's been removed. No request, scale down the pod. So it means that no memory, no CPU, nothing is used. Then what's happened if, for example, this is my backup cloud, and my primary cloud goes down. It will start sending requests to this secondary cloud, which everything is stopped. Let me send to this service a request. Now I'm sending the request, and you see, it's running again. It just started a new pod. So Knative is able to do this kind of things. Okay. Also, one of the great things that it can do, let me delete this. Delete pod, delete F. Is a scale up. So we've seen here that we can scale down to 0 when there is no traffic and scale to 1 when there is traffic. Also, we could in this case, I can annotate this service saying my target is 10, which means that for every 10 requests that I send to this pod, I will scale up 1 more pod automatically. Now, let's do this. I don't know if I've got Hey installed. Yeah, okay. Apply F, serving, service. Right. Now, okay. As I said before, all these things are present in the tutorial that with this link that I share with you. While this is deployed, you can see everything is explained here. And one of the great things is how to scale up. To scale up, I'm going to use one tool that is named Hey. Hey can be, as I said, used for creating traffic. In this case, I'm just going to do, or I'm going to send 50 concurrent users. And the link is this one. Now, what you're going to see is that this prime generator is being scaled up automatically. Just scaling to 3 instances, because I get it request, I just reach the limit, so I just add a new pod, then a new pod. I get all the requests, so I just get it on a spike of traffic, and if we wait for 1 minute, automatically it will start on deploying all this. So Of course, the final solution would be something like this, having Knative in all your clouds, and just have your pods and services there up and running, and then having a Skupper installed, and this pod should be a Knative pod. In this way, you are saving all the resources that you might require in terms of money, okay? Of course, just use Knative if you need to scale down. If you do not need to scale down, for example, because what you just want to do is have multiple regions, all of them interconnected, and that's all, nothing else, and all running, then don't use Knative. But if you're concerned about the billing systems of having multiple clouds, then Knative might help you on this. Let's read down. Just keep in mind, as I said, Kubernetes, it's a thing that's a really nice tooling, really nice, or the de facto, also the de facto tool for deploying microservices, and give you a really nice experience regarding hybrid cloud. Remember Skupper. Skupper, it's here for connecting all your services using a layer 7, so no VPNs, no firewall rules, nothing. It just installed and it works. In fact, in my Amazon cluster is a protected cluster, which doesn't let you run a lot of things, and it works. And then we've got here 3 examples. The first one, this one, oops, sorry, here. The first one is the one that I show you. The second one is exactly the same, but using Knative. So if you follow this link, you'll get all this, let's say, information of how to use Knative plus a Skupper. And the last one is this, hybridized to-do app. And this example is quite complex, but it works. And there is some script that you run some scripts and they are just deployed, which is using a to-do application, which has a database to store the to-dos. So you're saying, OK, I've got an hybrid cloud, but in these cases, we've seen a stateless application, but what about a stateful application when there is a database? And this application is using CockroachDB, okay? If you deploy it, you will be able to deploy to-do app in your Amazon cluster, in your Google cluster, and deploy the Cockroach cluster as well there, and you will have nodes in both of the clusters, in Amazon and in Google. And you could simulate things like, what's happening if the application goes down? What's happening if the to-do backend goes down? Then the traffic is automatically routed to another cloud. But what's happening if it's not the application? What's happening if it's the database of the cloud that goes down? Automatically, the data will reroute to the other cloud provider. You will put all the to-dos. And when you boot up again the database in the primary cloud, all the data will be automatically synced. So you're not losing data, and you're having the database installed there in both clouds, and both of them having the same content. And as I said, in a really, really easy way, because it's just a matter of installing a Skupper. And that's pretty much everything that I wanted to show you. As I said, my email and my Twitter, if you've got any question, just feel free to ping me. Thank you very much. Yeah, if there's questions.
Yeah, if there's any questions for Alex at all.
I will be around here now, so if you say, oh, I don't want to do it here openly, you just ping me outside, and yeah, no problem.
Cool. Thank you very much, Alex.
Thank you.
So yeah, we're going to there's a quick 5 minutes changeover, and then we'll get Andrew on. Cheers, Alex. Thank you. Yeah, so we're going to swap mics. Alex. So Andrew's going to talk about kind of how the default configuration isn't always ideal.
Yep.
And how we should probably have an understanding of how to change that, especially for those that put their hand up around using Kubernetes in production. Awesome. Over to you, Andrew.
Thank you. Hello, everyone, and welcome to this session on adjusting pod eviction timings in Kubernetes. Really quick introduction about myself. My name is Andrew Pruski. I'm a SQL Server DBA, Microsoft Data Platform MVP, and certified Kubernetes administrator. I'm originally from Swansea, Wales, but I've been living in Dublin, Ireland for about nearly 10 years now. So I came over from Dublin this morning. I've been up since 3 o'clock. I'm kind of wired. So if I'm talking quickly, I do apologize. My contact details on the slide there, at dbafromthecold and dbafromthecold@gmail.com. So if you have any questions after today, please feel free to reach out. I'm always willing to talk about this stuff. My blog's there as well, dbafromthecold.com, and my GitHub account as well. Loads of stuff on my blog about running pods in Kubernetes and things like that. And then my GitHub account. There's an exact QR code to my repo where all the slides and the code for the demos that we'll be doing today are all available to you. If you want to grab the code, you're more than welcome. So, bit of background. As I said, I'm a SQL Server DBA, and I've been one for well over 10 years now, actually. And I've been running SQL Server in containers for dev, test, and QA for, I'd say, about 5 years. Containers were a real game changer for us in the SQL Server world. When we got new versions of SQL Server, we used to have to spin up a VM, download the installer, install the package, play around with it. And then we'd have to blow that VM away when a new version came out, a new CTP came out, something like that, because they weren't compatible with each other. Those days are gone. It's great now. We get a new version out, we pull the image down, we spin it up, we play around with it, we blow it away. So it worked so well, in fact, that I started thinking, can I run SQL Server in a container in a production environment? And started playing around with it, and really it was starting to investigate running in Kubernetes. I did have a look at Docker Swarm at one point, but Kubernetes really did sort of win the orchestration wars, as it were. It was really the main player there. So that's what I've been working with, and having a look at mainly testing in Azure Kubernetes Service. Now, I've used Amazon's offering EKS a few times as well. I haven't played around much with Google's one. I have built my own Kubernetes clusters. If you want to check out my blog and you want to get Kubernetes up and running on a Raspberry Pi, you can do it. Have a look. It's take you through step by step how to get Kubernetes up and running on a Raspberry Pi, and you can play around with it there. So, also, I wrote an article a while ago about my old company called Ding, based in Dublin, Ireland. This is the company that I deployed SQL Server in containers for their QA environment. They used to have a refresh process of their QA environment where they'd have to blow away all the VMs, spin up the VMs, install SQL Server, and then deploy all their databases. It usually took about 45 to 60 minutes. Got rid of all of that, got their deploy time down to 2 minutes. A massive saving. And this is what really kicked off my interest in working with SQL Server in Kubernetes, and Kubernetes just in general. OK, so when I was doing my testing for SQL Server on Kubernetes, I started having a look at, basically, I'm DBA by trade. What we basically do is think about how do things break, how do things fail, and what happens when they fail. So I started looking at what happens when a node goes down. What happens to pods when a node fails? Now, this is testing Kubernetes inbuilt high availability. So what should happen is the node becomes not ready, and pods are moved. I say moved, but not really moved. A new pod is spun up on a node in a ready state. However, the default of that takes... How long has that been gone? All right. I'll unplug and replug. Please bear with us. All right, no worries. Well, something just happened with my laptop. We'll try again. No joy? So we're going to be doing some demos with this session, and I recorded my demos because we're going to be shutting nodes down and spinning them up. But also, I've only got half an hour, and I didn't want to have any demo failures.
You mean you didn't bring a new monitor?
Yeah. There we go. Is that up? Nope. Oh, we'll try another one.
I've got one as well.
Thank you. Oh, let's try this one. Wrong way around. Is that off? No? No, so we've got two guys at the back here. All right, no worries. They're video demos. I can't play them on. No. It's recorded.
Do you have the presentation, or do you just have the video files?
I have the video files, yes. I kind of need to stop and start, and there's 4 of them, so yeah. Yeah, yeah.
Thinking it was my dongle then.
It's not, no. Let's take this one out.
That was warm.
That does happen, yeah, but where's the... Thank you very much. Let's try it. I don't think it's the USB port, though. It's registered on here when I plug it in. I can see the screen change. Oh, I'm not touching that. Tap. Ah, there we go. Excellent. OK. Sorry about that, everyone. Bit of chaos engineering in action there. OK, so for those of you who just joined us, what we're talking about is testing stateful apps in Kubernetes. I'm a SQL Server DBA. I was wondering about whether I could run SQL Server in Kubernetes, and what happens when, say, a node fails in my Kubernetes cluster. So technically, all the pods should be moved, new ones spun up on a ready node. But by default, this takes 5 minutes. So OK, for a non-stateful app, who cares? You would have deployed a whole bunch of apps to your cluster, the node goes down, all the other apps take the traffic. Not a problem. For, say, SQL Server, where we can't shard SQL Server across multiple nodes, we have one node with its database, one pod with its databases, 5 minutes of downtime, it's not really acceptable. But let's go and have a look at what happens with the default settings for a non-stateful app. This is me in Visual Studio Code, so I'm just getting myself to the right place. This is not the right video. There we go. OK. So just me setting my location in Visual Studio Code. We're setting a resource group name. This is where my nodes live in Azure. This is against Azure Kubernetes Service. And there is my virtual machine scale set with 3 nodes in it. Your nodes in AKS are a part of a scale set, and that's how you can scale them up, scale them down. So if we do kube control get nodes, there we go. We have a 3-node cluster. OK, nice and simple. Let's see what happens when we start messing around with this cluster. So first thing to do is deploy a test application. We're going to deploy something really simple. We're going to say kube control create deployment test from an Nginx image. So we're just going to have one pod running in our cluster. Nice and simple. And to prove that I'm not cheating, I'm going to expose that deployment with a type of load balancer service, port 80 to port 80, so I can connect into my application from outside of my cluster and see that everything's working. There we go. That's all good. Right, next thing to do, view everything. And we'll go kube control, let's get everything. Let's just see what we've deployed. And we have our pod running, our service with the external IP, so we can use that to connect in. And then we have our replica set and our deployment, all looking good. So just one pod running with a service that we can grab its IP address with that big, long, nasty bit of code, and then drop it into, say, curl, and then connect to make sure we can connect to our application running in Kubernetes. So do a curl against it. Boom, there's the Nginx welcome page. Everything's working as expected. Fantastic stuff. So we've got our app running. We know it works. Let's start mucking around with this. So let's watch those nodes. Let's have a look at them. Say kube control get nodes watch. They're all in the ready state. But now let's jump into a new terminal. Just switch it over. Grab the node that the pod is running on. And thankfully, all we need to do here is just strip out a bit to get the virtual machine scale set name and a little bit of an instance ID. So we've got the virtual machine scale set name and the node ID, which is 9. And we can drop that into a Azure CLI command, and we can shut down that node. So we say AZ VMS deallocate, name, instance ID, and it's a resource group. We let that run. This part of the video I have sped up, because otherwise we'd be sitting here for a couple of minutes sort of looking at each other going, it's coming down at some point. So we're waiting for it, we're waiting for it. At some point, we will get this node in a not ready state. And there we go. Our node is now down. OK. So let's have a look at that pod. We go and have a look. We say kube control get pods. Well, we'll have a look at the nodes as well. There we are. Status of not ready. And then let's have a look at those pods. Still got the one pod on the node that is actually down. So at this point, our app is down. We can't connect in. We can try curling against it. If we do a timeout of 5 seconds, our app's down. OK, cool. So let's have a look at those pods again. And this part I have sped up again, because the default timeout before that a new pod is spun up will be about 5 minutes. So I didn't fancy we all sit here for 5 minutes and go, I promise it will work. I promise. So I've sped this little bit of the clip up just so that we can see that after 5 minutes, we will get a new pod up and running. So that is the default for pods being spun up on a new node when a node in Kubernetes is reported as down, 5 minutes. and we have the old pod of terminating. And it will always stay in that state while the node is still in the cluster in a state of not ready. We either need to remove the node from the cluster, sorry, or spin the node back up. So jump into the other terminal, do AZ VMSS start, spin that node back up, and again, sorry, chaps. Oh, it's back. Wait. I didn't touch it. There we go. So now we're watching our nodes, making sure, there we go, our node is back up and ready. So that node has been restarted. Confirm that it's there. There we go, all nodes are back up. And then we can have a look at those pods again. So if we have a kube control, get pods output wide, boom. OK, we've only got the one pod. Now that the node is back in the cluster and status already, it could report that it was terminated, and we now have our one pod running as before, the default, the desired state of our deployment. And we're testing back in, and we can connect to our application. So that's the default. So that's the default tolerations that we have in Kubernetes, 5 minutes. And for say, OK, I appreciate Nginx, who cares? You'd have had multiple pods running on different nodes. You could have connected into a different pod, and it would have served the application request. But for SQL Server, for me as a DBA, that's an issue. That'd be 5 minutes that my pod is, my application is down. I'm getting spammed with on-call messages, getting alerts going, you need to fix this, you need to fix this. So we need to adjust that. Now, there's two methods of doing that. We can, depending on how you built the cluster and the type of cluster you have, if you've built your cluster with, say, kubeadmin, you can set the eviction timeout on the API server. You can set your tolerations for not ready and unreachable down to, say, 10 seconds. You can then run the following code, sudo kubeadmin init, create a YAML file, sorry, sudo kubeadmin init, phase control plane, hit that, deploy that, and that will set 10-second tolerations for not ready and unreachable nodes across everything in your cluster. But the example I'm using, we're in AKS, Azure Kubernetes Service, a managed service. We don't have access to our API server. So what we need to do is actually add the toleration into the deployments. And we can just add these in to our deployment.yaml when we apply it, giving it 10 seconds for unreachable and 10 seconds for not ready. So let's go and see the difference. Here we go, back in Visual Studio Code, just setting my, and we'll have a look at our deployment. So kube control get all, this is the same deployment as the last one. There we go, external IP that we can use to connect in and test that our application is working. All righty, so let's go and grab that external IP and confirm. First thing we do whenever we do stuff like this, test that everything's working as is. There we go, Nginx welcome page. Everything looks good. OK, let's go now edit that deployment and add in those tolerations. So you say kube control edit deployment test, and you have to bear with me here. This is Vim, and who here is good with Vim? Oh, all right, fine. I'm terrible with Vim. So we cut this in. We'll drop down to the spec in the container. There we go. At the end, just before status, not there, Andrew. Next bit, there we go. And we can copy that in. Set paste, for some reason, isn't the default, so drop that. Add that in your own time, Andrew. Thank you, Andrew. And here we go. Save that, right quit, and we have edited our deployment, adding in those tolerations. So now what we can do is, same as before, same as in the last demo, we'll jump into a new terminal, grab the node that the pod is running on, and we'll shut it down. So we'll grab the node, get the virtual machine scale set name, and the instance ID, which is 9. And then same as before, using Azure CLI, just say Azure VMS deallocate, and that'll shut our node that the pod is running on down. Jumping back into the other terminal, and we can watch our nodes. And OK, fully admit, this part of the clip is sped up, because otherwise we'd be waiting for the node to go down for a couple of minutes. So I've just chopped it. There we go. Our node is now down. Excellent stuff. So confirm that. Node's not ready. And now let's have a look at what happens with our pods. I've not sped this part of the clip up. We're watching our pods, and boom, There we go. By adding in those tolerations, we've got those 10 seconds, the new pod has been spun up, our application is back up and running. We can test that if I get rid of that, just to confirm. There we go. We've still got the old pod in terminating state, which will always be that way until we either delete the node from the cluster or spin it back up. But we can confirm connecting into Nginx. Everything is good. OK, so by adding in those tolerations, we've had that new pod spun up a lot quicker than waiting for the default 5 minutes. So this was really sort of starting to tweak my interest when I was thinking about SQL Server and Kubernetes. Can I rely just on Kubernetes high availability? And by the way, in the background here, we're just spinning that old node back up to get rid of the old pod. So we're waiting for the node to come up. And the same as in the last demo, the old pod will be gone. But this was really tweaking my interest. It was like, can I start looking at SQL Server in Kubernetes and just using Kubernetes high availability if I can edit the tolerations like that? 10 seconds to be downtime? OK, it's not ideal, but I'll take it over 5 minutes. So, talking about stateful applications. This is where really getting into the meat of it now. The pods need to move to a new node, need to move to a new node in a short amount of time. So we've already got that sorted. We've got the 10 seconds, pretty good. But the storage also has to move as well. Well, I say move, but detach from the old pod and attach to the new pod. Otherwise, our new pod, even if it's come across and spun up because of the toleration, that pod will not spin up. SQL's trying to reference storage that isn't there. It's not going to come up. So no mucking around. Let's go straight back into the demos. So, same as before, we're in here, and we have a load of storage classes in Azure. We're going to use the default one. We're just going to go for the default storage class. I'm going to create a load of persistent volume claims. And I'm going to create them persistent volume claims, and we're just going to reference the storage. No reference to a storage class. We use the default one, and that'll spin me up my persistent volumes in the background. So you've got 3 of them. Really simple. Access mode, read, write once with SQL Server, and a size of 1 gig. So we'll deploy those. The default storage class is also wait for first consumer, so nothing's going to actually be spun up until I deploy something that's going to reference them. So we're going to create a deployment for SQL itself. Here we go, really simple deployment. 1 rep, 1 pod, the referencing the 3 volumes, and there's where they're going to live. This deployment also, I should have scrolled down further, has those tolerations in it as well of 10 seconds. So let's go and deploy that. And then we can have a look at that storage has been created. Oh, sorry, my bad. We're going to expose that deployment as well. SQL listens on port 1433. So we're going to expose that with a type of load balancer so we can get an external IP address just so we can connect in. OK, so that's been exposed. Let's have a look at our storage now. We've got our PVCs. There they are, all bound. And our PVs bound to our claims. Great stuff. OK, so storage is up. Let's confirm our deployment and our service. So kubectl get all. There's our external IP. Nice and simple. And let's have a look at those pods as well. So kubectl get pods, output wide. Just the one running on the 09 node. Cool, big, horrible, long, nasty thing to grab the IP address. I never do this in real life. I just sort of copy and paste and drop it in, but for demos, it looks kind of cool. And then let's create a database, just so I can show you and prove to you that the storage is coming across. We're going to just use the MS SQL CLI. It's a nice cross-platform tool for connecting into SQL. Create that database, and then do a select name from sys databases, confirm that database is there. And there's our database. OK, so same as before. We are going to go and jump into a new terminal, grab the VSS name, and grab that node. And then we're going to shut down that node. So clear that out. And here we go. OK, so that node is now going to be shut down. Jump into the first terminal and do a get nodes watch. Full disclosure again, this part is sped up, very much so we can just continue on with the presentation. The node is now not ready. Confirm. Yep. OK, that node is now down. OK, so let's have a look at those pods. Do out pods gets right, and I was too slow. That pod is already coming up. We put the toleration of 10 seconds, but it stayed in the status of container creating. This is because of an issue with the storage. The pod has moved, but the storage has not. So if we grab that pod name, and then we do a describe on that pod, we can see what's happened. We can do the describe shows the events of the pod, and we can see we've got multi-attach errors for volumes. The pod is already in use by a different pod itself. And that's where it's going to stay until we do something about that old pod. And the only way we can get rid of it is to spin the old node up or delete it from the cluster. So we need to jump back into our second terminal and start up that node again. Personally, I would just kill the node from the cluster. But for demos, spin it back up. So again, waiting for the nodes, and I'm speeding this up again. There we go. Node is now reporting. Oh, come on. Just to keep me on my toes, and yourself. OK, where did I skip that on forward? Or? There we go. OK, so the node's back up. And that pod is now still in container creating. It takes a long time. It takes a couple of minutes for the storage to move to the new pod. So again, it's extending that period. And if we have a look now, there's our pod, and it's on our new node. So if we just recap what's happened here, we've created a load of storage using the default storage class in Azure Kubernetes Service. We have spun our pods up. They're all working fine. A node has crashed, something's happened, and started reporting as not ready in Kubernetes. Because of our tolerations, a new pod has tried to spin up on a healthy node. But it has been unable to spin up purely because it is trying to reference storage that is attached to a pod on a downed node. And that's where that pod is going to stay. It will stay in container creating. Meanwhile, you will be getting paged like there's no tomorrow purely because your application is down. OK, so if we have a look at the pod now, and just to confirm everything, now that the new pod is back up, we can connect in, and boom, there's our database. So not ideal, really. This one has really been having me scratching my head about what I can do about this. So there are options out there. So what can we do out there? And one option I did find is something called Portworx. It's made by, everyone heard of Pure Storage? It basically deploys a bunch of stuff into your Kubernetes cluster that allows to get over this issue. What you end up with is a storage class in your cluster that you can use to create your volumes, and that doesn't have the disadvantage of the default storage class in Azure of the pods, the storage being still attached to a down pod. It will actually move that storage for you, basically bringing your app up if there's an issue with the node that it's running on. So let's have a look at that in action. So starting off exactly the same again, back in Visual Studio Code, setting our location. And then we have the Portworx setup here. OK, so it's not too involved. They do give you step-by-step instructions. Basically, what you do is they'll give you a big, long YAML file that you deploy, and it goes and deploys a whole bunch of stuff. I mean, you can scale it down quite a lot, and it will give you just the bare bones, but you can also implement things like monitoring and stuff, which I would highly recommend you do. But it'll give you a big, long YAML file, and what you end up with, in the end, is a storage class that you can reference in, say, your persistent volume claims or persistent volumes to create your storage. And there we go. We have it down the bottom there. And I'm really bad at naming things, so I called it PX Portworx MS SQL SC storage class. And there we go. And it also deploys. We just check in a whole bunch of stuff there. What it does is it deploys pods to each node. Oh, I missed that. I was just going to point out the restarts of those pods because I've been doing these demos, spinning them up, spinning them down. So that was me breaking Portworx, not Portworx breaking. And so here's our storage again. So here's our persistent volume claims. And we go in each time we have, the only difference being this time we have an annotation specifying that we are going to use our Portworx MS SQL storage class instead of just leaving it as the default. It's keeping everything else pretty simple. Read, write once for access mode, and I'm just going with a gig of storage here, just because I'm spinning up a test. I'm going to create a test database that is about 8 meg. So there we are. There's our storage. We can deploy that nice and quickly. There we go. And this isn't wait for first consumer. This is immediate, so storage is going to be there straight away. So we can check our PVCs. There we go. And our PVs. Boom, and I'm going to get rid of that. And there's our claims bound. Excellent stuff. So we have our storage this time. So now we can go and we can create our deployment. And this is exactly the same as the previous one. Nothing different. One big, long, simple deployment, one pod, volumes, volume amounts. Excellent stuff. And, of course, I should have scrolled down further, the tolerations at the bottom. So we've created our deployment. And now, same as before, we're going to create a database, so we're going to expose that deployment. Port 1433 to 1433, type of load balancer, so I can get that external IP and connect into SQL Server. OK, there we go. We've got it there. Everything looks good. Our pod is up and running. We've got our service with external IP. Deployment's good. Replica set. We're pretty good. There we go. Pod on node 09, same as before. Great. OK, so grabbing that IP address again, and then this time let's create another database. And this is a database that I'm going to test, again, with the great naming conventions. It is called test database. Cool. Final thing, there we go. There's a database. OK, so let's get into it now. Let's go and switch into the other terminal, and let's shut down that node again. So grabbing the node the pod is running on, grabbing the VSS name and the instance ID of the node, dropping it into our Azure CLI statement, VMSS deallocate, and we'll shut down that node. Cool. Full disclosure again, this is sped up because we've been waiting for a couple of minutes, but let's watch those nodes. And there we go, our node is now not ready. Cool. Excellent. OK, so our node is down. This time, let's have a look at these pods. OK, this is not sped up. There we go. Container creating, same as before, but now, because we're using that Portworx storage class, we have our pod up and running on our new node. So we have our applications back up. Our SQL Server instance is back up and running. We still have that old pod in a terminating state, but we have our new one up and running. So let's grab that new pod name. And I made a mistake here with my little command there, so I need to go and change that 0 to a 1. Grab that pod name, and let's have a look at the events of that pod. So kube control describe pod. Oh, get pods. Yep, this is me mucking around because I made a little mistake at the top. Grab the pod name, Andrew. Come on. There we go, Andrew. All right, and now we can describe the pod. Boom. Now, we still get some errors there, which isn't great. But we can see at the bottom there, the pod spanner, and we can connect in. So let's finish off by just grabbing that VMS start, starting up the node so we can get rid of the old pod. Jump into the other terminal, watch the nodes. Again, of course, sped up. There we go. Node is now up and running. Confirm, 3 nodes up. Get pods. Still got that terminating pod there. It does take a couple of seconds for that pod to get, a couple of minutes can do, for the pod to go away when the node is reported as ready. But eventually you'll see a couple of events there. That means that pod is now gone. So if we get rid of that, boom. Our pod is up and running on our new node. And fingers crossed, our database is actually there as well. So we just do a select star from sys databases. Boom. There is our database. So by using tolerations and a third-party option such as Portworx, we can get high availability for a stateful app such as SQL Server, which doesn't have any actual Kubernetes high availability features itself, running up in, say, Azure Kubernetes service. So you can't just use, say, the default settings when you deploy your apps. For stateless apps, not a problem. Stateful apps, you have to consider what happens when a node goes down, your timings for your tolerations, and then what also happens with your storage when new pods are spun up on a new healthy node. OK. So I hope you enjoyed that. I hope that was informative. I've got a couple of links for you here. That QR code will actually take you to my GitHub repo where the slides and all the code for the demos are, so you can go and replicate this yourself if you want to. And I've got a couple of other things there. my blog post talking about this as well, and then the taints and tolerations documentation for Kubernetes. Thank you very much. Oh, if you have any questions, I'll be hanging around a bit for a little bit, but I'm going to take this mic off now.
Won't work, mate. Especially with that. Like, Jesus.
Hi, everyone. So let's see where we can take this. So I'm a developer advocate at Elastic. I mostly do events like this today. If you have any other questions, just don't be shy. Okay. If you've never seen our software, this is what it looks like. That's something, I'll come back to that at some point in the demo. But the common question we get is, what is the perfect data store solution? And what is your answer? What is the answer that everybody gives is, normally it depends, especially when you're a consultant and then you want to bill a lot of hours afterwards, then your answer always starts with it depends and it's very complicated. But unfortunately, it is really complicated if you have a lot of trade-offs to consider. And this talk is really about the it depends and the trade-offs that you have around data stores. So let's dive into that. Picking the trade-offs is really the gist of this talk. Because even though some vendors try to sell you or promise you their magic, there is no magic in the background. There is always a trade-off that you need to pick. Which leads me to the Cap Theorem. Who knows the Cap Theorem? Okay, that's not so many. We'll quickly go over that again. So the Cap Theorem started off as this paper, or actually there was a talk by Eric Brewer, and then these two people, Seth Gilbert and Nancy Lynch, they wrote the paper about it. And while it's called consistent, available, partition-tolerant web services, it's not really about web services, but anything that is stateful and keeps data. So it will apply to any database or any data store that you have. And the basic idea is you have these three attributes, and the paper basically says you can only have two of them. What are these three attributes? You have consistency, or a consistent state, which is a total order of all operations. So it basically looks like you run one operation after the other. So even though you run many things in parallel, there is a total order of like one after the other. So at any point in time, it's clear which operations have been before and which operations have been after, which is important to get like how much money is in my bank account. It needs to be clear like which transactions have gone in before and after to be like, this is the consistent state that I have right now. So it looks like you had been running that at a single instant, even though we're talking about distributed systems here and what makes them interesting. Then you have availability, which basically means any node that is reachable over the network has to respond, and the node cannot say like, I'm not sure what the state is right now, I will not answer, because that's another attribute that you want to have in a distributed system. And finally, partition tolerance. Your network can lose arbitrary messages. Those of you who say like, well, our network is so good, that never happens, either you have been exceptionally lucky or your monitoring is not good enough. Because there were some nice papers by AWS, Google, and Azure who said like, these were all the things that are going wrong in their data centers on a daily or weekly basis. Like they know how many nodes, racks, switches, or even entire availability zones they lose on average. And it's quite a few. So this is a thing that will hit you at some point. Just saying, our network is so good and our nodes are not so good, it will not happen, is not really a thing. The trade-off here is that you need to pick at most two of the three. If you don't pick explicitly, something random will happen if things go wrong in your system. And then you will have to live with the consequences. So the idea is you have these three attributes. You can only have two at once. So you can see there is no middle here, basically. But you can only have this overlap between them. So you can have a consistent and available system that might not have partition tolerance. And you can pick the trade-offs, and you can pick like that overlap. But you need to pick, and you cannot have all three. By the way, it's not guaranteed that you have two. You can see you could also be only in one if you don't implement it correctly, or you could even be outside here if you make very bad implementation mistakes. So it's not guaranteed that you will have any of these attributes for sure. Like I said, partition tolerance is not a thing that you can choose, but it will be there in any distributed system. And the other thing is that, unfortunately, consistency is an overloaded term, because maybe you've seen consistency in ACID, atomic, consistent, isolated, durable, like in the transactional sense. And in the ACID sense, it's a predicate. So it basically says, I'm going from one correct state to the next correct state, which might be like, you have a not null constraint, you have referential key integrity, you have like a specific data type. You're only moving from one valid state to another valid state. Whereas the consistency in the Cap theorem is about timing. It's like, this is the order of events. And unfortunately, those two consistencies mean different things, even though they're both called consistency. And if you want to explain the Cap theorem to your kids or your parents, you can do that with Robinson Crusoe. So Robinson Crusoe is on his lone island, so he's basically partitioned from the rest of the world. And then he has to decide, am I consistent or am I available? Let's assume a ship comes by and asks him, like, who is the current queen or king of England? Because I think Robinson Crusoe was British, if I remember the story correctly. And then Robinson Crusoe has to decide, am I consistent or am I available? Because if he answers, he's available, but he might not be consistent with the rest of the world, because his answer might be outdated. Or he could be consistent, and then he doesn't answer because he decides, well, I'm not sure who is the king or queen of England right now, so I'm not answering. Then he is consistent, but then he is not available. And that is really the gist of the Cap theorem. So the Cap theorem is, for a paper, it's not very mathematical. It's really just like more of an explainer. The assumption is, for example, you have a three-node cluster. And you write data into 2 nodes here and 1 node here, and the network in between them breaks. So you have the 2 nodes here are isolated or partitioned from the other node here. And if you write data into these 2 nodes here, this node here doesn't see the other 2 nodes. It knows that it's partitioned, and then it also has to decide, am I accepting reads or writes? Then I'm available but not consistent. Or am I rejecting operations? Then I'm not available, but that node would be consistent with the rest of the system. And that's really the entire proof or idea of the Cap theorem, that you need to pick those trade-offs. Does anybody recognize the island? No, it's been a bit too long maybe, but it has been in one of the newer Star Wars movies. And I always like to build my examples around Star Wars. So we will get into how this actually works in an actual system for some Star Wars examples. You can, by the way, break the Cap theorem, but that doesn't necessarily give you a useful system. So if you write your data to dev null, so you basically throw it away, it's kind of always available, it's consistent, and it's partition tolerant, but it's still a useless system. So you can kind of break Cap, but not in a very useful way. Which leads me to the so-called Fab Theory. The Fab Theory doesn't have a fancy paper. It's something one of our colleagues at Elastic invented, Mark, showing him at his favorite hobby. And he has this theory that, similar to the Cap theorem, where you can have 3 out of 2 at most, that he has 3 other attributes that you can have 2 out of 3 at most. And his attributes are fast, accurate, and big. That's the Fab theory. So fast here means you have near real-time processing of data. It's not a batch job. You don't have to go for a coffee to actually get back the result, but it's near real-time. So it's anything up to, I don't know, depending on how patient you are, 1 or 3 seconds maybe, but it's not much slower than that. Then you have accurate, you get exact results rather than approximations. We'll get into that because that one is confusing, like why would I ever work with inaccurate results? And finally, big, you need to parallelize your data. And I really don't like the term big data because it has been abused so much. So we will try to not say big data anymore. We will just assume big here means it is using multiple systems. So it's distributed over multiple nodes, and that makes it big. So I think fast is quite clear. You wait for the response. Big, it's distributed over multiple systems, clear. How is accurate a thing? Like, how do I even get to a useful system if it's not accurate in the result? So let's see how that works. My examples will use Elasticsearch, but there are lots of systems that implement that in one way or another. But I'll show you how Elasticsearch sometimes trades in the Fab theory some accuracy for more speed and distribution. The only thing you need to know about Elasticsearch is that the so-called unit of scale is a shard. So basically, you have some data that belongs together, and you break it up into so-called shards, which is like one part of that data. And one shard can reside on one node, so that's how you distribute it over multiple nodes. Does anybody know where the term shard is coming from? Because it's quite widely used in distributed systems for data. Like I think MySQL and other systems call it shard as well. Does anybody know why it's called a shard? And there might be multiple theories of that, but I'm believing in this one. Does anybody remember this one? Who is old? Yes. What is that? Yes, it's Ultima Online. How old are you? No, you don't have to answer it. It's fine, it's fine. So it's a computer game. You can see it looked a bit different back in the days, but the story, and this article is actually from back in 2009, that there was an evil wizard, and he stored the world in a crystal, and the crystal was shattered into multiple shards, and that is allegedly why data stores picked up that shard concept, that a piece of the data is like one shard from that crystal, and that's where the term sharding is coming from. But that's just like the side story of where sharding is coming from. So let's look at the term segregation. Term segregation is like, which terms are the most common in my data set? And I've said, we'll use Star Wars. So my Star Wars data set is this. This is from the very first Star Wars movie that came out. So like back in the, I don't know, whenever that was, 80s. I'm not old enough to remember. But when that came out, in the first movie, Luke appeared 64 times in the movie, R2 31 times, Alderaan 20, etc. So somebody did that counting. And I'm basically creating one document for each of these terms. So I have 64 documents with Luke. And I distribute it over 5 shards. So I could have it on 5 nodes. And then I want to do that counting. And obviously, my counting is kind of expensive if I have 1 million terms or 1 million documents to count, and then I need to aggregate it on each node, and then one node needs to collect 1 million or 1 million terms. So there is some optimization in that, and we'll get into that in a moment. So I split it up into 5 shards, and one document looks like this. I'm basically saying, put into the index Star Wars a document that is called Luke. So I have 64 documents with Luke's and 31 with R2, etc. So these are my documents. And then I want to run that aggregation to see which are the most common terms. Just to give you an idea of what I have here. So this is just running a search operation, and it tells me I'm looking for Luke because I know what to look for here right now. And it tells me that there are 64 Lukes in my data set. And now I run this term segregation, and this is basically saying run an aggregation for the most common term. That's the name I've picked, and it's a term segregation on this field. The word is like where I store the Lukes and R2s and whatever. And the size 1 here tells me I only want to have the top 1 document, so I'm only interested in the most common term. Forget about all the other ones. I want to know what is the most common term in Star Wars. Size 0 down here might be confusing, but this is only telling Elasticsearch I don't want any of the actual documents. I only want the aggregation, so only the count. I'm not interested in any of the documents. And when I run this, it will actually tell me that it found 60 Lukes, which is kind of weird, right? And so this is wrong. And to put that into Star Wars, so it's kind of weird, or it should be impossible that it's 60, right? So let's figure out why we counted wrong, or what is the optimization why we count wrong. So I have cheated a bit. So I have skewed my data set. So we have something called a routing key, and that basically determines into which shard we write the documents. And I have, for the first 10 documents, I have used an incrementing routing key, and for the 54 remaining documents, I've always used the same routing key 0. So these 54 documents down here will all go to the same shard. And this is how the documents are assigned. So basically, you hash the routing key, you count it modulo the number of primary shards, and this will tell you onto which shard the document will go. Why do I hash it before using the routing key? Any guesses? So I have even distribution of the data. So I want to avoid a hotspot. If you just use a name, for example, and you might have a hotspot in like the first letter on the naming, it would all go to the same shard. I have kind of artificially created it here, that the shards are very unevenly distributed, just to skew my data. And as you can see here, what happens is that on one shard I have 71 documents, and on another shard I only have 26 documents because of that routing key. And how the term segregation works in the background is, the assumption is I'm taking size, the number of documents I wanted, multiplied by 1.5 at 10, and this is how many of the top n results I get from each node before I do that total aggregation. So what was size in my example? 1, I only wanted the top 1 document. Multiplied by 1.5, I think if I remember correctly, that's rounded down, plus 10, so I end up with the top 11 documents per shard. Each of the 5 shards send its top 11 documents, and then on the node that is coordinating that aggregation, it will combine those and then give me the total number back. So what happens is, because the data is so unevenly distributed, on some shards, the looks are not in the top 11 documents, and thus I forget some of the looks or don't count some of the looks. That's why we're missing them here. What you can do is, here, I'm adding a parameter to say, like, tell me the error of the counting. So what this gives you is, it counts the looks, and it also says, by the way, there might be 4 looks missing. And this is actually the correct number in the end, because what it does is, it knows the number of how many occurrences of a term do you have in the top 11 results, and then it knows if Luke is not in the top 11, there could be like 2 more Lukes in there in position 12, 13, whatever, so we might be missing some Lukes here. And this is telling me the error count, and it also tells me up here, in total we missed 10 documents, and there are 228 other documents than Luke. Now, what I can do is, I can set the chart size to 20, so I'm getting the top 20 results per node. Since I only have 16 documents, that should be or will be accurate. If I run that now, it will then tell me, now I found the 64 looks, and I have 0 documents that are missing. And I have traded a bit accuracy for fast, because now it's slower, because I need to aggregate more terms and I need to combine more terms, but it is more accurate. So fast and accurate are like 2 things that I'm trading here. It's still the same big, because it's still 5 shards and potentially 5 nodes, so it's distributed over them. But this is what we have set up here. So this is the term segregation and how the trade-off works for the term segregation. So we have seen this. In the interest of time, I have 2 other examples, and I'll only run through one. Which one do you prefer? So I have either cardinality aggregation. Cardinality aggregation is like, how many unique terms do I have in my data set? Or I also have an example that shows for full text search and like ranking documents, like how relevant they are, there is the same artifact. Any preference of which one you want to see? Full text. OK, then we'll do full text. We'll jump into full text then. So does everybody know how a search engine works, like Elasticsearch? So if you have a database is very good at this black and white, something is a match or no match. A search engine is much more about the shades of gray, or like the relevancy of like, how relevant is this document? It's not just necessarily about direct hits, but it's more about like, how good is a document matching to the thing that I'm searching for? And the grandfather or grandmother of how this works is so-called Idf, which says, and I think I missed a slide here. OK, I'll just explain. No, this is the slide that I want. TF-IDF is what I want. How TF-IDF works, and it has been replaced by something called Bm25, which stands for best match, and is the 25th iteration of the best match algorithm, but the approach is the same. So what happens is, you have 3 attributes in Bm25 or TF-IDF. The first one is term frequency. So if I'm searching for Luke, and one document contains Luke once, it's less relevant than another document that contains Luke 3 times, basically. So it's the square root of the frequency of the term that I'm searching for, which basically looks like this. If I'm searching for Luke, and I have 1 Luke, it's this relevant. If I have 5 Lukes, it's more relevant. And you can see there's one difference between TF-IDF and Bm25. TF-IDF is just the square root, and it keeps increasing, whereas Bm25 is like, once you have found 5 Lukes, is that really so much worse than 25 Lukes? Not really, so Bm25 just basically stops that steep increase and just flattens out the number of occurrences and how important they are. Second part is the inverse document frequency. The assumption is what is rare is valuable or important. So if Luke appears over all the documents you have in your data set very few times, Luke is much more relevant. If Luke appears very rarely, if Luke appears many times, it's very common, and it's not as valuable. So that is how that curve approximately looks like. So Luke appears only like 60 times, so it's pretty valuable, whereas, I don't know, Stormtrooper might appear more times or whatever, so it's less relevant. And finally, field length norm, which assumes the fewer words or tokens, as we call them, you have in a field, and your search term appears there, the more relevant it is. So if you have a short title and Luke appears there, it's more relevant than if you have a long text body and that contains Luke, because it's just lots of words and then it's less relevant. And you can combine that and get your data. And one thing you need to know for Elasticsearch is how we actually query data. And how we get data is we call it query then fetch. So it's a two-step approach to actually get any data out of Elasticsearch. So we have a cluster with 3 nodes, and to keep it simple, I only have a handful of shards. So I have a shard 1 and a shard 0, and I have replicated it for high availability, but that doesn't really matter so much here. So what is important? If you send a query to Elasticsearch, the query will go to this node here. As an example, this is called the so-called coordinating node. The coordinator will then go to the other nodes and say, like, in your shards, do you have loops? And then each shard will say, like, yes, I found these loops in my data. And then the coordinating node will combine those results. And it doesn't send the results back to the client yet. It actually says, like, I'm looking for the top 10 documents of Luke, for example. It sends a request to the other shards and says, like, give me your top 10 looks. And it will then say, like, I have, for this search query, I have, these are my top 10 documents. The coordinating node will then say, like, OK, I've got overall, I've got these top scores, top 10 scores overall. And it will then say, like, I'll fetch the 3 documents from here, for example, and 7 from here, because these are the overall top 10 documents. And that is the second step. So this is the fetch step. Basically, in the first step, you're only saying, like, these are the scores and the document IDs. And in the second step, based on the document IDs, we just retrieve the documents from the nodes, get the full documents to the coordinating node, and send that out. Can you already see the problem, why this will create a problem with TF-IDF? Or let's run the query to show you how this behaves. So I'm running my search query here. And what is surprising is I find my 64 looks. This is fine. What is surprising here, I have one look here, which has a score of 3 point something, or 3.2. This has 3.1. And then as I scroll further down, I see it's totally the same document. And the relevancy of this one here is only 0.7. Why is this look less relevant than the other looks? Yes? Yes. So the inverse document frequency was counting, and it's only counting within the shards by default, and it saw that in one shard there are many looks, so it assumes that look is common and not that useful or valuable, whereas in other shards it's only appearing once, and that makes the look very valuable, and then the score is higher. Is that a desirable approach or attribute of a search system? Not really. So what you can do is you can add a third step in your request, which is called DFS query then fetch, and I think it's something called distributed frequency. So it's basically, in the first step, it's going to the shards and says, like, tell me how many looks you have, and then it knows overall there are 64 looks, and then it will kind of like even out the statistics across all the nodes of the cluster. And if I run this, then you can see I still find my 64 looks, and now all have the same score of 1.5. So here the statistics are evened out. And just to skip through that, this was easy. And following this, there are normally 2 questions that people will ask me. First one is normally, how much performance will this cost? And my favorite comic for any performance-related thing is this one here, where you can see under similar conditions, one system is much better than the other. So we have killed the house cat, and the squid is doing fine solving the puzzle. And this is pretty much what most people are doing when they benchmark their competitors. So you can always benchmark for your scenario and your data and your hardware what makes sense, but it's very hard to make a general statement. And secondly, in our documentation, it says DFS query then fetch is really not recommended to be used because it shouldn't be necessary. The assumption is normally you should have enough data over all your shards that it evens out naturally. Otherwise, you normally either have too many shards, even though you don't need them, or you have done something weird. And I have done something weird that the frequency is so unevenly distributed. That's why we're kind of like stuck in that weird place. So the solution to this would be, I can use a single shard, which is, by the way, also the default in Elasticsearch. What trade-off am I picking now? I'm suddenly not big anymore, right? Because I'm trading the distribution over multiple nodes. If I have a single shard, it can only be on one node. It will be fast and accurate, but it will not be big in terms of distribution anymore. So I'm changing the trade-offs now. And what you can do then is, by the way, Simon, one of our co-founders who is based in Berlin, he always said, use a single shard until it blows up. And only once that happens, figure out how many shards you need and how to scale that up. So you can, I take the same data, I rewrite it to write it into an index that I called starlet war, so the little star, with a single shard. And if I search for Luke without the DFS query, then fetch attribute, will the score be the same across all the documents now? Yes, it's only a single shard, so the frequency is the same across all the documents. So this will just give me the same documents. It's all 1.5, whatever. If I run the most common query, so the top n that we've seen before, will that give me an exact result now? Yes, because in the top 11 results that I'm getting, Luke is the top one, so this will also be an accurate one. Only in the cardinality count, where I count the cardinality, that would still not be accurate. But you can look it up in the slides afterwards, how that works in detail. But this was kind of a cheap move, I want to say, because now we're not big anymore and we're only fast and accurate. But we have kind of given up on that scaling factor. So to wrap up, it's all in the trade-offs, and you can build systems that have the right things for you, but you need to pick them consciously and explicitly. Otherwise, your system will potentially do things that you don't expect. For some people, that Elasticsearch has this trade-off in terms of like, oh, it's not accurate, but it's fast and scalable, is right. For others, this is totally a bug, and they're very unhappy about it. And you can then tweak the parameters to potentially make that work in a better way than you want. So I hope you remember the Cap Theorem is kind of like the grandfather of all trade-offs, and it's like this 2 out of 3. And we have taken it, and it's not it doesn't have a fancy paper like the Cap Theorem, but the Fab Theory is kind of the same thing. You have trade-offs, you need to pick the right one for your system to actually make sense out of your data. And that's it for having fabulous data. Any questions? Otherwise, take some stickers. Thanks a lot for joining, and enjoy the rest of your day.
Cheers, Philip.
Sure, my pleasure. Let me, this was mine, this was yours.
Okay, great stuff. Thanks everyone for attending. So this is the last session of the Cloud Native Data Management Day, like a little mini subset of sessions that we put together over the last 2 hours. And really what I wanted to focus about is it's all about the data, with a focus around the data service and where that lives. Obviously, we're going to be talking about the cloud native part, but then also some considerations. If you've been here for the whole 2 hours, it's about really, from a data management point of view, how are you protecting those workloads, or how can we protect those workloads, specifically if they're running in Kubernetes. So just to introduce myself, so I'm Michael Cade. I'm a senior technologist at Kasten by Veeam. So Kasten, I'll touch on this in a little bit of the session, is really focused on Kubernetes backup. So first and foremost, the backup and the recovery of those workloads, those stateful workloads within your Kubernetes cluster. Then I'm going to show you just that it doesn't have to be inside the cluster as well. We might be leveraging a PaaS service such as RDS to be able to protect those workloads. So we might completely leave our Kubernetes cluster as a place where we run our stateless workload, but then we leverage a PaaS-based solution to give us that state or look after that data. So I've been in the data management space for far too long. It's generally the most boring part of anyone's conversation or budget. So I get the tail end of the 2 hour session that we have, and just talking about some of those strategies around being able to protect those workloads. I think it's all fair to say, like, there's quite a lot of us here, and hopefully there's some on the stream as well, like, data's pretty important. Like, we're either writing our applications that store some sort of data. There's not many stateless applications that don't have a requirement, apart from maybe static websites, that don't really have an element of data or a use case for some way of putting data into it. Just a few examples of data and how it's intrinsically growing at a rate of knots, and we have to think about, well, what do we actually have to protect, and what don't we need to protect, regardless of where they are as well, because obviously we bring in things like edge numbers to this as well. So, but the common denominator to that is data, where regardless of the platform that we're thinking about, whether it's a virtual machine, whether it's a cloud-based workload, or whether it's a cloud-native container that is leveraging some sort of data, the data is the common denominator that we have to consider, and we have to think, do we need to keep it? Do we not? Do we need a copy of it? Do we not? There'll be some logs, maybe, metrics, maybe, that you don't need, but notice that I keep on saying maybe, because it depends how important those logs are to your application. You might need them in 24 hours, or you might need them in a week, or you might need them in 3 years. So really, it really depends, and I think actually all the speakers have said that when it comes to architecturally making a decision on where you store your data, it really depends. It depends who you are and who you're speaking to. Whether you're a developer, whether you're sat in the middle from a DevOps point of view with a focus on the developer and the experience around that, or whether you're on the operations side and you're actually thinking about where that data is and how it lives. So the key part here is that, and if you're a developer, you don't really generally care too much about the platform, the infrastructure, the operations side of where things live. So whether it's a physical system, whether it's a virtual machine, whether it's a virtual machine in the cloud, leveraging IaaS-based systems, or we can go one step further with PaaS and SaaS in there, or whether it's a container, and whether it's just a container on its own, or whether it's a part of a container orchestration engine, such as Kubernetes. I'm not specifically talking about just Kubernetes there. It could be something like HashiCorp Nomad or another Docker Swarm, for example. And I think the key part here is, so the data lives across all of them, or can live across all of them. And the important part there is none of them have gone away. Like, some of us are going to be very early in our journey, depending on what or what programming language you're even developing in. You could still be massively dependent on physical systems, and then virtualization and cloud. So we're all at this like tipping point or a journey of where and where do we pick and where do we put our data services that we require for our application. That built out horribly, and then, okay, we now need to think about, well, which one do we choose? Do we need to make that as a developer? Do we need to make that as an operations? Do we need to make that as the DevOps, the SRE? Or is it dictated to us? Or do we pick from a catalog that gives us the best, or that looks like it's the fastest storage available for our database? And then going back to my original point is, I kind of always start off by talking about that first point is, well, do I need to back up and restore that data? So if I don't need to restore it ever, then I don't probably need to back it up. So that's the first question. And then we have to think about, okay, what does that recovery look like? And what am I recovering, or what is my recovery plan for? Is it a disaster? Is it things go really bad for the front end or for the whole application? And do I need to consider having that in a different location? And then probably the most, especially as you get further down that line of all the different platforms, when it comes to containerization, it gives us a much more flexible way of being able to redeploy or deploy our workloads, our applications in all of the different places. Kubernetes gives us the capability, or container orchestration gives us the capability of really running in a lot of different places. So application mobility is key and kind of goes intrinsically with your data management process, because it gives you the ability to actually lift and shift those workloads that maybe if you were a physical machine or it was a virtual machine, you're very much reliant on the operating system. So you're very much having to move gigs of data to move it from site A to site B, which is a massive pain. People do it. People are still doing it, that lift and shift approach into public cloud, IaaS, etc. But when it comes to containerization, that application mobility really gives us a way of being able to upgrade or move around, and we're no longer tied into one provider or one hardware option that we have there. So one of the key parts, and if you can read that on there, down the bottom here, so if we think about backup and restore in a containerized environment, we have to start thinking a little bit differently, but it's another story, and I'll touch on this later as well, is that it's the same but a little bit different all the way through those platforms. So whether it's physical, virtual, cloud, or cloud native, we still have to consider how we protect those workloads, those our data services, our databases, or in general, it could be the logs. Why is that beeping? And then we also have to think about role-based access control. Who has access to this? How do we provide a self-service capability of being able to simply either hook into an API or adopt this or integrate it into your, is that mine beeping? Oh, cool. Phew. We have to think about how we integrate backup into our pipelines. How do we integrate it into our continuous deployment, or generally deployment rather than the integration point of view, because that's where we're going to start going from version 1 to version 2 of the application. And that external data source is not being managed by that version control, because as soon as you're putting stuff into that database, it's no longer in our repository, right? So we have to start thinking about that. We also then need to start thinking about, okay, we're going to scale out or scale up our application. We have to think about, or how is it going to perform, and how are we going to protect it at scale, especially containers. I don't really care about the container. I care about the data, but I don't really care about that particular container that might be gone within a minute. So I can't leverage that, but I can leverage the persistent volume claim that should always be there, right? And then I have to think about performance. Okay, as a backup, I have to be the set and forget. I have to go and sit here, and I just have to pounce whenever something's changed. I have to understand what's changed to be the most efficient I can be. And then polyglot persistence, or I need to be agnostic, is probably the easiest way to coin that. How can I protect over all of the different variations of Kubernetes that we have, OpenShift, EKS, AKS, GKE, on-prem, upstream, etc.? How do we make sure that we've got the ability to protect our workload, our application, regardless of where it lives? And then how do I then start looking at the disaster recovery on top of that from a recovery point of view? How do I go cross availability zones? Again, it might be different storage tiers that we have available to us. So how do I automate that? How do I make that simple? How do I schedule that? So start thinking about all of those different platforms to consider the use cases around that. Well, one, do I need to back up and recover my workload or my data? And then where to, and what level as well. Like, you might have a Kubernetes cluster that is completely safe, maybe. Or maybe the application that runs on it, the data is maybe not that important. It's just gathering metrics and logs. But that mobility, I believe, is going to be that way of being able to transform what that application looks like, that desired state, on the fly or as part of an automated process, is probably the key part that we're at least having from a Kasten point of view when it comes to talking about data management. So that then leads us into the first demo that I'm hoping is just going to start playing when I hit the next tab. But if we think about going from one cloud to another, and we might have different storage classes within Kubernetes, I want to be able to recover that as fast as possible, whether it's automated, and in this I'm just actually manually going through the process, but think in the back of your mind that this could be completely automated on a scheduled basis or even dynamically based on some sort of action that happens. So before I do that, if we think about, if we think about a typical 3-node Kubernetes cluster, we've got a control plane, we've got our node 1, we've got a node 2, we've got an external web interface, and we have a persistent volume claim where our important data lives. Obviously, our containers, our pods can spin up, spin down. I believe it's a stateful set that gives us that database and gives us that persistent volume claim. Yeah. So if you think about my stateful application, or my mission critical application, I should say, obviously, is Pacman here. So first of all, let's just make sure that we have some critical data within our database and in our persistent volume claim. So then we're going to log our mission critical data. Now, this is just going to a Mongo database in the back end. It's using a Node.js front end. And you can see I've got loads of mission critical data. You can see as well that I'm running this on K3s. So I'm using this on maybe a local development system. And I'm just proving a point that I can now take all of this data and I want to move it into, I think I want to move it into EKS, but I can't quite remember. But you can see here, okay, there's my Pacman namespace. This contains my service, my pods for my front-end Node.js app. It contains my persistent volume and my stateful set. And then I'm going to jump into EKS, so AWS. I have a cluster ready and waiting for me to scale up my application. But I also want to take all of that test data with me. You can see here, we don't have any Pacman namespace. So what we're going to do is we're going to leverage Kasten K10 to go and take that in a consistent fashion, and we're going to go and deploy that into our environment. So we have an import Pacman policy. We're going to restore after the import. So again, we've got lots of characteristics that we can bring here. But what we're going to do is we're going to change the storage class, because I'm using K3s here, and it might be storage class cheap. And I'm going to go to AWS EKS storage, which might be expensive. So I'm just changing that on the fly. But the most important part there is I'm going to be in control of that PVC. I'm going to import it from object storage. So prior to this, I'm taking backups of my mission critical application, and I'm sending that to an S3 backup location. And I've created this import policy. Now, if I dive into that EKS cluster, you'll see here that I have that policy in place, and I can hit run once. You can specify again, you can automate this whole process, but that would be a pretty boring demo if I just showed you here's one and here's the other. So what I'm doing now is that I'm going to start restoring that, or migrating, or cloning, whatever way you want, whatever the use case is, right? Because it could be the other way. It could be, from a development point of view, I now want a copy of that data locally on my K3s cluster. So it could be that you're wanting to clone this as well as migrate it, or actually it is a recovery. I want to actually bring up my, something bad has happened to my K3s cluster and I want to bring it up in EKS or another place. So while I was babbling on, everything's coming up, as you can see. And now if I go to that AWS, the load balancer IP address, I should get into my, and the spoiler alert is that I know that it's going to be there. I recorded it. And then we're going to see our Pacman, our Node.js front end. And if I you'll see that, first of all, it tells me that I'm in AWS now, so that tells us that. If I jump into high scores, though, all my mission-critical data should be there. Happy days. And really, again, just to highlight that data management isn't just about the fire, flood, and blood. Like, it's also about how can I migrate data and clone data to take advantage of that data? How can I get insights into my business by being able to expose that to another service? Like, maybe it's leveraging Google services to just glean that little bit of information, quickly spin up, and then get rid. So storage is a bit of a minefield when it comes to Kubernetes, but I would say that over the last few releases, the Kubernetes release team has given a lot of focus around storage and data particularly. So when you've got your application, and again, we look back at that Pacman app, we have a stateful set which has a pod, and our app that is connected to a persistent volume claim or a persistent volume, and then we have our external storage. So this is the consistency. That is where my Mongo database, my back end, is going to be living. And then we also might have a front-end service, although an application might just be using a Kubernetes cluster just for infrastructure purposes and just want to have that stateful set and want that application external, maybe in a virtual machine that hooks into this and just takes advantage of a stateful set or a deployment within Kubernetes. So when it comes to storage, this is where, like I mentioned around Kubernetes and the release team have put a lot of focus around storage and data. A few years ago, I would say more than 2 years ago, there was the in-tree provisioner. And this was where we were constantly waiting, or constantly is probably not the right word, but we were waiting for the Kubernetes release so that we could enhance any of the functionality within Kubernetes around storage. So that was obviously had its delays. We were releasing 3 times a year, but these were volume plugins, and it was kind of the first iteration of, well, we can run stateful workloads in Kubernetes, though. So that was the first light bulb moment for that. And then along came the container storage interface that gives us the ability to have a storage plugin that we can do out of band. We can have any storage vendor can plug into those APIs and allow us to take advantage of those. So just to explain this, and without getting into the weeds, you've got your external storage, and of which there's over 100 CSI external storage drivers available out there. But basically, from Kubernetes side, you have your control plane, your nodes, and then within that, within the main core Kubernetes code, is you have your external provisioner, you have your external attacher, and your driver. So think about them as APIs that are exposed out of your Kubernetes cluster or out of your nodes. And then you have your external component from your storage vendors that hook into those so that you've got the ability to do things like volume snapshots and another task, being able to resize on the fly, which was the latest one within 1.24. So that really gives us the ability to enhance what we're doing from a storage point of view within Kubernetes very quickly. I'll also give a shout out here to Cozy, which is the object storage interface as well. So that gives us the ability to then leverage object storage as well as block and file-based storage that we see here, which is generally what we see from a CSI perspective. There's other different types of storage within Kubernetes as well, so I have to mention those. So if you think about config maps and secrets, that's what generally could give us a config map is going to give us a pointer to an external location or an external resource, or maybe even an internal resource, but generally it's going to give us a pointer to something. And then we're going to have secrets. Secrets are sensitive objects that give us the ability to access those potential config maps or those resources. So I mentioned at the start as well, we're seeing more and more customers that are using maybe a Kubernetes cluster with a stateless app and then hooking into a database service, such as Amazon RDS. So for this, I'm using RDS as an app. So again, what I want to be able to do from a backup point of view, I don't want to have a point solution that just goes into AWS and protects that, because then it knows nothing about the rest of the app that's in Kubernetes. I'm hoping this is running. Yeah, it looks like it. So this is using Postgres as the back-end database. And then if we come in here, you'll see the RDS app that I have. If we go and look inside of that, this will see it. So we have a config map that gives us access to that RDS instance. So that contains all the information, the URLs and the UUIDs that we need. And then also I should have a secret that gives us the access to it, the IAM control into that. So again, DB creds gives us the accessibility into that. And this basically shows that we've got the ability to leverage that PaaS solution within there. So we have Kasten deployed, and we have a policy that's created. I'm purposely not showing too much around the product, but if you want to see more, we've got a stand over there as well, and we can dive into any of these details. But basically, we have a policy created to take a snapshot on demand, because if I did it scheduled, we'd have to wait either a long time or for a reason to run it or actually run it. And then I want to export it. So this kind of goes back in time. I never went through this beforehand with the last demo, but this enables us to take a very fast snapshot locally, so really fast recovery point, but alone, that's not going to give us the ability. If that storage dies, it's not going to give us any recovery point. So what we also want to do is export that out to S3 compatible storage or AWS S3 maybe, and have a copy of that data out of band so that we can always recover from that. And then a few other settings in there. We also use Canister. Canister is an open source project maintained by Kasten, and that's focused on the application consistency of that data. So it's going to go, so for Postgres, it's going to go in and it's going to trigger the action set around PG dump, and it's just going to allow us to have a copy of that PG dump in a consistent fashion into our object storage location. So what you can see here, we're just triggering AWS APIs via that import policy. But now what we're doing is we're going to have visibility of the whole application. Half of it's in Kubernetes, half of it's in, or half of it could be in Kubernetes, half of it's in AWS RDS. So I hope I speed this up because it takes about 12 minutes every single time we do it. And that's leveraging the AWS APIs with that credential, with that config map, with that, with those secrets to access that. So you'll see up here first, we're taking that backup. Backup in Kasten K10 world is a snapshot. So I do have a front-end app. It doesn't live inside the cluster, but obviously it could. So we have our DVD rental system, and we have all of our important data within there. And what I'm actually going to do, and this kind of goes back to that point around, okay, I want a clone of that important mission-critical data that is running in RDS, but I don't want my 100 developers to have 100 RDS because that's going to cost me a fair bit of cash. So what I want to do is I want to spin up a K3S cluster or another cluster, and I'm going to run through that import process of being able to bring all of that data out of RDS and into stateful sets, bringing it all inside a cheaper storage tier locally is kind of the high-level overview of what we're doing. So we're first taking a backup, so that's going to be using EBS snapshots within AWS, if that's still in the EKS cluster, or local snapshots for really fast recovery. And then we're going to export out into object storage. So the video is only 5 minutes long, so we've got a minute left, so it should speed up very quickly. So once that backup's complete in that consistent fashion, we're then going to leverage that snapshot, and that's what we'll use. So we're not having to stop and quest the data twice. We're actually just going to leverage the snapshot to export that out into object storage. Oh, as if by magic, it completed successfully. We definitely weren't standing here for 10 minutes. And here, if we refresh, it should be all back and available, all consistent, all of that good stuff. So next thing I want to do, so RDS, I can access this. Think of this as my production front-end database. This is what my version of Blockbuster is using. I don't know if that translates to everyone, but the ability to buy and sell DVDs. Now I want to restore it, but I want to bring it back locally for my developers to use that data and maybe glean some information from it or just leverage that data. So I'm going to take my exported copy and I'm going to choose, well, where is this going to go? So maybe I just bring it back locally, or maybe I bring it back to another cluster. notice here that I'm bringing this back to GKE. So I'm going to bring it all back as a stateful set within there. So, oh no. So when it comes to, like I've mentioned a lot about stateful applications, and it's not just really the database is completely important, but we start thinking about host names, IP addresses, the security around that, the secrets, the config maps, and all of that important stuff. When it comes to stateless applications, the amount of customers that we also speak to where they've got complex environments, and yes, you all should hopefully have some source code somewhere that allows you to deploy that app again if something bad was to happen. But just taking a quick backup of all that config map, all of the configuration and the manifest and everything that goes with that is another use case that we see out there in the field as well. And remember, I said this at the very beginning, and hopefully you can see that, but I said about data management, regardless of the platform, so whether it's Kubernetes, whether it's cloud, whether it's virtualization, whether it's physical, it's kind of the same, but it's a little bit different. We have to, especially when it's cloud native and distributed, we have to think about a few things a little bit different. But ultimately, you still need it because there's no magic button around, well, if a failed application, whether that be the database or whether that be the whole environment, we still need to recover that. If we need to migrate that data from A to B and there's a lot of reasons why you might migrate from one service to another. You might go because of cost. It might be because of risk. It might just be simply because of scale. But then also, how do I optimize it? Well, I can go to a bigger and better, faster cluster. So I want to be able to migrate my whole entire app, not just my source code. I need my external data as well. And then we need to protect that data in a similar or an SLA. So kind of the key bullet points, the 5 key bullet points. 1, protecting the persistent storage. There's no magic button within Kubernetes. We still need to have that protection. I mentioned around stateless and complex environments. So where you've got 300 potentially stateless applications within one cluster. How do we protect that? Or how do we recover that very quickly? Protecting individual stateful workloads. It might be that we run multiple or one important database or data service that we have to completely focus on. Stateless configurations, things like load balancing, and then configuration of the stateful workloads as well. It's all well and good being able to go in and get that PG dump, which we can absolutely do using Canister, open source project, but wrapping that all around in an orchestration model for backup or for data management is the key part there. So the focus, and I should take Kasten out there. The focus really for us, if anyone's deploying anything into Kubernetes and looking from a data management point of view, we have to look at the whole application. There's no point in us just looking at the data service. There's no point in just going to protect RDS. We have to think about the whole application, and that includes things like the config maps, the secrets, the services, and everything that builds up that so that we've got the ability to restore that wherever we want. Another key part of Kubernetes is the freedom of choice. Like from a distribution point of view, we can pretty much run Kubernetes anywhere. But also from a data services point of view, no one should be locked in because, whatever that reason may be, to using a particular data service. But regardless of what that data service is, we have to consider how we protect that data service. So the freedom of choice around that, and then the storage. I mentioned like one of the use cases was being able to move from one storage to another, cheap to expensive, or I should say maybe slow to fast. That's probably more PC around there. But being able to migrate that and not being locked into any of these choices or not being locked out of anything else. So I think that's time as well. So the final thing is to share a resource around Kubernetes, free learning resources around that. So not necessarily Kasten from a product point of view, but that QR code will take you to, I think we've got about 7 labs now that talk about all things data management. It talks about the system volume, storage security, and also just getting a Kubernetes cluster up and running as well, and giving you the key fundamentals when it comes to running workloads within Kubernetes. But yeah, I know that's time. So if there's any questions, I'll be hanging around down the back. But hopefully that was useful. Thanks very much.